At 10 a.m. on Black Friday, a single cache entry expires. In milliseconds, hundreds of threads hammer the database. The site slows to a crawl. Orders are lost. That's the thundering herd problem, and it can be avoided. Caching is fundamental for read-heavy systems, but the real challenge is keeping the cached view fresh without crushing the origin. We'll dissect the 4 application-level patterns, then confront the stampede and the eviction decisions. The most common pattern is cache aside, also called lazy loading. The application checks the cache. On a miss, it loads from the database, stores the value, and returns it. The cache is just a side store. This gives total control, but writes leave the cache stale until the TTL expires. In read through the cache itself, loads on a miss. The application treats the cache as the data source. Write through writes to the cache and the database synchronously. Consistency is high, but every write pays the latency of both operations. Write behind flips that. The application writes only to the cache, and the cache asynchronously flushes to the database in batches. Throughput soars, but a crash can lose the unflushed tail. Reads may see stale data until the flush completes. Invalidation is usually time-based. Every key has a TTL. The stampede happens when a hot key expires, and dozens of concurrent requests all see a miss simultaneously. Each one queues a database query, replicating the same work and overloading the origin. Picture a key that gets 10,000 requests per second with a 60-second TTL. At expiry, in the first millisecond, perhaps 50 requests arrive before any reload finishes. The database sees 50 identical queries, then more, until the cache is warm again. The simplest defense is per-key locking, often called single flight or request coalescing. Before hitting the database, we acquire a lock for that cache key. Only the winner performs the load. All other waiters then receive the freshly stored value. The load happens once, no matter how many concurrent callers. Probabilistic early recomputation, like the xFetch algorithm, prevents the key from ever expiring under load. Before the true TTL, each request computes a random chance to trigger a background refresh. The probability grows as expiry approaches, so the cache is regenerated while still serving stale enough data. A simpler trick is TTL jitter. Add a small random offset to every TTL, so many keys don't expire at the same instant. That spreads the load and avoids correlated stampedes. Some caches and CDNs support stale-while-revalidate. When a key expires, the cache returns the last known value and asynchronously fetches the fresh one. The caller always gets a fast response, and the database sees a paced refresh instead of a spike. Eviction policies decide which keys to drop when memory is full. LRU removes the least recently used item, tracking recency. LFU counts accesses and evicts the least frequently used. Choosing the wrong policy can evict a hotkey and trigger a cache miss avalanche. Sizing is critical. A cache too small thrashes with constant evictions, dragging hit ratio down. A cache too large wastes expensive memory. Measure your working set size and provision for peak, not average, to maintain hit ratios above 90%. Caching isn't always a win. Data with a high write-to-read ratio, strongly consistent real-time numbers, or low latency sensitivity won't benefit. Adding a cache doubles the problem of the source of truth and adds staleness risk that may not be worth it. Consider a flash sale for a limited sneaker release. The product detail page is served from a cache key that maps to a complex database view. At the peak, second 50,000 requests hit the same cache key. With a 60-second TTL, on expiry, all 50,000 requests per second start pouring in as cache misses. The database connection pool saturates, P99 latency spikes to seconds, and the whole checkout flow degrades. The fix is a single flight lock mapping each product ID to an in-flight future. When the key expires, only one thread queries the database and builds the view. Every other request simply awaits that future. The database sees exactly one query per 60 seconds instead of hundreds per second. With probabilistic early recomputation, we can do even better. The system occasionally refreshes the key at the 55th second mark, so it never truly expires under load. Staleness is bounded, and the database never sees a spike. Write-through gives strong consistency, but writes are slower. Write behind decouples writes for speed, but a node crash can lose data. Single flight reduces database load, but adds complexity and may block callers if not implemented with a timeout. Stale-while-revalidate trades a few seconds of staleness for lower latency and load. Use cache aside for standard read-heavy workloads with acceptable staleness. Pick write behind for high-velocity ingest like clickstreams. Use single flight for any hotkey and probabilistic recomputation for keys where stale data costs little. In production, monitor cache hit ratio, miss latency, and the number of concurrent loads to the same key. Set TTLs with jitter, protect every hotkey with single flight, and test Stampede scenarios under load before Black Friday. Catching reduces latency and load, but introduces the synchronization problem. Choose the right pattern for your consistency needs. Defend hotkeys with single flight or early recomputation. Size the cache for the working set, evict wisely, and never ignore the thundering herd. It will appear at the worst moment. Thanks for watching. I hope this one was useful. See you in the next video.